Hi, my name is Henry Reed, and today I'll be going through my implementation of the COMP3003 coursework. This coursework uses the Fashion Mint dataset, which is a dataset consisting of 10,000 28 pixel by 28 pixel grayscale images, each of the images representing one of 10 different types of clothing. Labels and features array are derived from the data variable, which isolates the first column for the labels array and the other 784 for the features array. The features array is then normalized between values of 0 and 1 to speed up convergence. The dataset is then split into training, testing, and validation sets, which using two CV partitions. The first partition features splitting the dataset into training and testing, which is 8% training and 20% testing. And then the second split splits the 80% training into 75% training and 25% validation, which maintains a split of 60% training, 20% validation, and 20% testing. The Y labels are then converted into categorical to prevent the classes having a relation between each other, where the model used a 10-fold cross-validation technique. For the neural network, it takes an input of 28 pixel by 28 pixel by one color channel. The grayscale images only have black and white, so there's only one color channel. Sorry, these are the results. And then this is the main layers in my CNN. There's 3 blocks, each block consisting of a convolutional layer for feature extraction, a batch normalization layer for stabilizing those features extracted, and a activation function which introduces non-linearity to the model, allowing them to learn complex patterns. I used max pooling for the first 2 layers in order to downsample the feature maps which extract the strongest features from each of the input images. Didn't feature in this because they've already been reduced twice, and if I do it again it will just progressively slow down the softmax layer, leading to inaccurate accuracy scores. So this is the structure of the CNN seen here, and then these are the training options for the CV, which uses the SGDM, a learning rate of 0.01, a 4 complete passes of the dataset, and shuffling at every epoch. So for each of the 10 folds, split data, reshape the data, train the model, and calculate the accuracy of each fold, where the mean accuracy and standard deviation over all the folds will be calculated, seen here. From there, I do one final kind of thing for the model, which trains it and tests it on the testing set, calculating the probability, calculating the confusion matrix, from that confusion matrix extracting the average, accuracy, precision, recall, and F1 score, as well as specificity for each of the classes, while as plotting a ROC graph, getting the area under the curve and the loss entropy, which is seen here. The confusion matrix is this one, and the ROC graph is this one, and I forgot to show this is the training progress. For naive Bayes, PCA was done to reduce the dimensionality as it took too long to run the model. This was done about calculating the cumulative explained, which which maintains a range of 95%, following a similar structure to the K folds. For each of the 10 folds, split the data, fit PCA to the training fold, apply PCA to the training and validation folds to reduce their dimensionality, train the model using the kernel distribution, and then calculating the accuracy of each fold, calculating the mean accuracy and standard deviation of all the folds, which is seen here. Then running the final model, calculating confusion matrix, performance metric scores, area under the curve, cross entropy, which you can also see here, followed by ROC for the naive Bayes model and the graph which shows the number of principal components that are required to have 95% variance, and the confusion matrix. Thank you very much.